All right, how's it going out there, folks? So yesterday we chatted about Earth's history and how time was organized and a little bit about the evolution of creatures over time. Today we're going to talk about how scientists start to figure out how old rocks are relative to one another, right? To date them in a sense, try to get a number on it. It starts out with relative dating, and that's a comparison. And then it goes into absolute dating, where you can actually get a number from it. So we're going to start with relative dating today. And no, I'm not talking about taking your, your brother or sister to the prom there. Not that kind of relative dating. I cracked myself up. So anyway, check out these pictures. And you can see a lot going on here, right? You got things crisscrossing. Over here, it looks like there's some layers missing. And we got to try to interpret what's going on. That's the whole idea, to figure out how old things are in relation to one another. All right? So normally we start out with a little comical approach on which teacher is relatively older than the other. Now, I certainly wouldn't go around and revealing anybody's age, but just to give you an idea, that's a pretty good relative age scenario where the oldest would be around here and the youngest maybe over here. I'm just kidding. They're all mixed together. You'd have to put them in a relative age order. So if you want to pause and give that a shot, we can joke around about that in the meeting a little bit. But on a more serious note, so here we go. Relative age, dating, figuring out how old something is compared to a surrounding event. Rule number one, sedimentary rocks start out flat, right? Original horizontal, and they stack like pancakes. That's how they start out. They don't always end up that way, but that's how they start. So the oldest one would be on the bottom, right? The youngest one on the top. Okay. The next part, right, the law of superposition, right, says that as well, where your youngest should be on the top unless there's been changes, and we're going to talk about those changes. Okay? Uniformitarianism, the idea that if it happened in the past, it's happening today, it'll probably continue to happen in the future, so you can kind of get an idea of what to expect in the future by looking at the past. Okay, the past is the key to the present. All right, so anyways, this is one of those exceptions, law of cross-cutting relationships. So here you have 1, 2, 3, 4 layers, the orange, probably the oldest, right? Purple, the youngest, because it's on top. But what if there's some pressure applied or some heat applied and tectonic forces take hold and you get a fold? Well, didn't the fold come after the original rocks? So you say, all right, so the original rock is older, right? So you got 1, 2, 3, 4, and then the youngest thing that happened, the most recent thing that happened, is this folding scenario. Okay? So there's your folds. Now all of a sudden we get more pressure here and it folds even more. That's called overturning. And now look what happened. So this older layer is absolutely on the top, right? So it would be oldest, middle, then youngest, and then things would get kind of crazy. So you have to keep an eye on that. And if you only had a section of this sample, you might get the age of it wrong. You have to take a step back, look at the bigger picture, right? They call those overturned or recumbent folds. Then you get, there's an actual picture of that. Okay, then you get a scenario like this where it kind of tilts it upwards. And of course, that's simply tilting. And of course, the original rock is older and then it gets tilted. Okay, and then here's a different kind of diagram where you had your original rocks. And all of a sudden something cut through, right? Maybe an igneous intrusion. That's what this is trying to show you. And these red marks, or whatever the magma touched, it changed, it metamorphosed. Okay? So when you talk about that, that's an intrusion. Here you have a fault. Now the fault is the youngest thing because it cut through everything, including the intrusion, right? It affected everything else. So in this case, now the fault is the youngest thing. All right, and there it is. Your faults and intrusions. And here you can see a lot of different faults going on from earthquakes, right? The cracks must be younger than the actual rock itself. Okay. So here we go. Started out with RYCZ, right? Oldest to youngest. Then comes an intrusion. So now this is the youngest. And if something happens to that, then this will no longer be the youngest, right? The next event will. Okay? You can see these metamorphic lines. They call that contact metamorphism. We'll talk more about that as well. Here you have the magma shot all the way out. It escaped the Earth. So it's no longer an intrusion. Now it's an extrusion. It exited the Earth. And if you remember from igneous rocks, this will cool off faster, have smaller crystals because it's an extrusive igneous rock. Unlike this one, is stuck in the ground. It's kind of like in that thermos, in that container. It takes a long time to cool off. The crystals would be much bigger here. Okay? Now you get M that gets deposited on top of this extrusion, and an untrained eye might say, oh, that never left the Earth. No, it did, because this rock has small crystals. There's no contact metamorphism on top. M must have been deposited later on. Okay, so the puzzles get a little tricky. You got to look for those little details. All right, that's a classic extrusion. Okay. If you have fragments or pieces of rock, well, these pieces came from another rock, so they got to be older. If they get cemented together like a conglomerate, make a new rock, well, keep in mind that each piece that's cemented together came from somewhere else, from some time in the past. So these little pieces must be older than the glued together rock that you found today. Okay, then there's an unconformity. So watch carefully. Here's your clouds forming. You get some rain, the erosional agent. Watch what happens to M and a part of Z and a part of J. That washed away. So watch again. This is the way it was a million years ago, let's say. And you get tons and tons of rain, wind, weathering, breaks it down, and now you're left with a rough surface, and you're missing a lot of rocks, right? They've been eroded away. That's an unconformity. And when you bury it, now you have a buried, eroded surface. And they call those unconformities. So make sure you get that into your notes. It represents a missing part of, history. It's a break in the time sequence. And you have to realize that something happened between P and Z. All right? And then you try to figure out how many years that represents. Okay. So here's another one. Follow it, follow it. I'll play it again, don't worry. This is what you have today, but obviously it didn't form that way, right? We're going to go back. It formed like this, original horizontality. Then it was folded, uplifted, weathering and erosion, followed by deposition. And now you have a buried, eroded surface, aka unconformity. Okay? So if you got to hit pause, rewind, play that again, go ahead. But that's classic of what you would find on Earth's surface over millions and millions of years of changes. Okay? That broke it down into 4 sections for you right there. This is what it actually looks like. You can see this was deposited on top later. This must have been a lot earlier. You can see there's a little fold going on there. So definitely there's another layer there you can see. A lot of changes happened because it all started out horizontal, right? Original horizontality. This one here, you can see these layers were tilted, but this one is not. So this must have come after all of the tilting and the weathering and erosion occurred. There's another unconformity right there. Okay? All right, so these are classic region-style diagrams. Let's check these out. They'll ask you, all right, what's the oldest thing in this diagram? Well, your eyes should jump to the bottom. Normally, that's going to be the oldest. Well, it looks like that's a type of rock there, right? If you look at your reference tables, the sedimentary chart, that's a sandstone. So the sandstone would have been the oldest thing. The youngest thing, well, let's see. Younger, younger, younger. But then the fault came, so that was younger. But then this happened. The intrusion affected everything. So this is the youngest thing, the igneous intrusion. Let's try this one. Oldest thing, again, eyes jump to the bottom. Right now you have shale. You can check your sedimentary chart for that. Then came the limestone, then siltstone, then sandstone. But then what happened? Well, was it the intrusion or the fault? What happened next? It's the thing that, well, take a look here. So this cut through all the layers. That must have happened last. So this must be in between there, right? The youngest thing affected everything. So your oldest is your shale, and the youngest, the fault, because it cut through everything. That's called the principle of cross-cutting relationships. All right, so I'm going to give you some diagrams to practice with. Do it that same way I did. Put your eyes to the bottom first, usually going to be the oldest, and then work your way to the top to find the youngest. All right. And, of course, there's a couple of summary questions that follow. All right. Take your time. Work hard. I'll meet you back in the meet.